All right. Let's wait a couple of minutes. All right, let's start. Um, so, as usual, if you have any questions, feel free to write in the chat box. And you can also unmute yourself at any time and interrupt me if you want to ask a question by speaking, by talking. Today, my plan is to finish the week 1 slides that are posted by Ozoja on CENG477, all sections, as section 1 material. I'm using the same set of slides, so whatever Ozoja posts as lecture slides, you can also refer to them. So my plan is to finish this first week of lectures, which is basically a very textbook material. We are not going to discuss any algorithms, so this is the least the part of the course that I least like, which is lots of material saying, okay, images are like this. There's human visual perception. I really want to get into the rendering part and the algorithms part, which is going to be a lot more fun when we start talking about ray tracing. But still, we need to discuss our output, which are images. So how can we generate images that are like real images that we see in our eyes? So also, how do we represent color? What kind of color spaces are there? And the voltages on the display. The display device contains the pixels with some, it changes the intensity of the pixels with some voltages. There are different channels, red, green, blue, or different type of, I mean, I don't know the hardware of the display that much. But what happens is that the main thing that the summary of today's lecture will be how we represent an image as a discrete set of pixels. So an image is something discrete. We will not have analog displays in our. I mean, there are analog displays, but usually these days we have discrete displays with discrete pixels. So, and those pixels, how color is represented on those pixels, how intensity is generated by changing the voltage on this hardware, and how this voltage change in the voltage is not linear. The way we perceive intensity, brightness, is not linear with voltage. Therefore, there's something called gamma correction that is applied to get rid of this non-linearity. Why don't we want something non-linear? Because it's easier to think linearly, especially, for example, if you have some color values that change from 0 to 255. If you have 1 byte to display the intensity of some color, all right, you want 255 to be the brightest and 0 to be none at all, and you want 128 to be the middle brightness. Okay, so it's good to or something between 128 and 255, the middle of those two numbers, we want at 75% brightness. So thinking like this linearly is better, is easier. but voltages are not like that. So therefore gamma correction is applied to the voltages on the display to make it more linear. Also, perception, human perception is also, there are non-linearities, there are differences between different color channels. We don't perceive brightness the same way as blue and red, for example. Also, we know that blue acuity is lower. Acuity is the, so I'm writing it in chat box. Acuity is the process of perceiving detail. Uh, we perceive detail worse in blue color. Red, we can perceive detail in red color better. We are going to talk about these things today. Okay, so it's not related to basically the rendering part of this course, which we will focus more on the remaining weeks. We will focus on this part. So we will see algorithms basically that solve this rendering part throughout the semester. Most of the semester we will talk about this. But today we are going to, the first week is devoted more to images and displays and perceiving this light field as the human perception. And in some of the weeks, we are going to talk about how we represent geometry and material, the interaction of materials with the geometry, with the light. We will talk all about this in detail when we talk about rendering. All right. So today, as I said, the plan is to finish this first weeks of slides, which are not algorithm related that much, but it talks about the details of what our outputs are going to look like. So here I'm going to go over the overall pipeline of a computer graphics application. So the main input to a computer graphics application, as I said, is a virtual world. And in order to see something in this virtual world, first there need to be objects. These objects, usually they should have some geometry, which are represented as triangular meshes or quad meshes we have seen previously. This is called modeling. So they have some geometry that we need to get as input. Also, different objects may have different materials, meaning that some objects may be shiny, some objects may be non-shiny, matte, and also the interaction of these different materials with lighting. We may have lights, pure white light. We may have green light. The light itself may have a different color. We may have point light sources, spotlight sources, unidirectional light sources. I mean, we have the sun, for example, but at night, for example, we have street lights. So how do you have these lights? How do you model them in a virtual scene? That's also important. Also, in order to see all these things, the geometry and materials and the interaction of these material objects with the lights around them, without an eye, without a camera, nobody, they are there for nobody to see. All right, so therefore we need some camera or a virtual eye that looks into this world. And you know, this to describe this viewpoint, we need its position. Where is the camera? And also some intrinsic parameters like field of view. What is the field of view angle that it sees, or which direction it's looking at. So we need all these different degrees of freedoms that are called extrinsic parameters of this camera. We are going to talk about this. So, and after that, after we set up a viewpoint and we set up a field of view angle and an image virtual frame, virtual retina in front of this viewpoint, we will be able to do the rendering. All right, and the dynamics apply to all of them. If you're going to have animation in your application, like a computer game or an animation movie, have these dynamics. You can change the geometry. You can make things explode, for example, all triangles go different places. You can have particle physics. The geometry may be very complex, and you can apply some physics rules to change the geometry, like springs or different forces acting on, for example, how do you model the wind acting on a bunch of leaves, tree leaves. So you need some physics. How this dynamics involves lots of physics, and some game engines, for example, come with physics engines in which these are implemented, and you can just drag and drop, use these them to your application to be able to use them, like collision detection, how the geometry is affected by this collision, elasticity, things like that. So it's really there are lots of things that you can model in real life that involves lots of physics in terms of these dynamics. The materials can be changing. As I said, the light sources can be changing in terms of intensity, in terms of location. So the dynamics apply to all of them. The camera may be moving in the scene, flying through over a terrain, things like that. All right. So the first thing in a rendering overall pipeline, we apply these dynamics on the input first. And at this point, everything we get a snapshot of our scene. The dynamics are applied, but at the time of rendering, we should just take a snapshot of all of those dynamics and then make the rendering as if the scene is static. So this goes on in a very fast manner, 60 frames per second. At the next, after the image is generated, we apply the dynamics again, change the geometry, material, lighting, or viewpoint, and do the rendering again. So this rendering pass, a single rendering pass, at some point it takes everything as static. It gets these inputs and then produce this image as the output. So there's a question. Oh, that's a very good. So the light, is it a geodesic? So the path that light follows through, are we going to, no, we're not going to consider any general relativity or anything. Okay, so I mean, since we're usually rendering in a very small, I mean, in terms of the virtual worlds that we display, I mean, if you have an application in which you try to visualize the entire galaxies, you may need to take into account these, or maybe if you're trying to view the whole world. I mean, there are two things. First, whether the light follows a straight path or not, and also whether the Earth is flat or not. All right. I mean, the Earth's flatness is something. I mean, it's light. Earth is still very small compared to how light travels, but these are really things that we just ignore when we try to visualize a world that we see around with our eyes. I mean, if you try to just see around, take a look around, you don't see more than like 1-2 kilometers ahead, and in that sense, you can assume things that are flat. Light always follows a straight path, things like that. But it's a very good question, seeing that, I mean, if you try to visualize galaxies, or I mean the solar system, we need to maybe get rid of this assumption that light travels in a straight path. So you may need to take into account the curvature of space-time, but that's really too advanced. Usually, I mean, there are much more advanced things other than just the light path. We need to. This question really brings a good subject that at some point, when we are trying to model these interactions with geometry, light, materials, we need to make abstractions. We need to make simplifications to do this at 60 frames per second. Because if we really want to generate a very accurate physical model of these things, we need computation time. And this computation time will not allow you to do this 60 times per second. Sometimes we try to do abstractions, we simplify things, we assume certain things, we make abstractions, and sometimes we cheat. All right, that's another thing. So we cheat because we have the power to cheat when we are displaying these images. For example, when I say cheat, for example, the actual geometry may not be curved. Imagine a sphere that looks like this. I mean, it doesn't look like a sphere, but you want to represent this view this sphere like the surface of a piece of orange. Okay, so the surface of orange is not smooth, but if you have a perfect sphere which is smooth, it will not look like an orange. In order to make it look like an orange, if we also have quantum computers, I really also wonder what quantum computers. We also need some quantum GPUs, graphics processor units on quantum computers. I think it's going to take a lot of time to see something like that, but at least if we can have something like that, we will see more and more detail. Actually, the reason that we have very realistic images and we have much more quality games these days that look like real images is the development in hardware. I mean, the GPUs, they can do these things. They can implement dynamics, geometry in a very fast manner. The developments in the hardware allowed us to make these computations faster and faster and faster. Therefore, we can lift off some of these assumptions and we can put in more detail, we can put in more accurate physics. All these can be put in if you have better hardware. And these days we see these things actually. All right, so here, as I said, as we have these things, the rendering, we will be able to render more quality images. So here today we are not going to focus on this rendering part. We are the first weeks of this lecture, the first week of this lecture, focus more on the output. How do we represent images? What are pixels? How do we represent color on these images and things like that? All right. So here, if the light field, a light field basically is something that is around us. I mean, we really receive a light field. Okay, so there's light everywhere, and light interact with objects, and when you're looking in this thing, so a light field basically is something continuous, and we sense that by with our retina, with our eyes, and our brain actually perceives. So seeing and perceiving, getting the signal, sensors. The retina is sensor, but everything is perceived in the brain. We can perceive geometry, movement. For example, certain sensors are better at perceiving motion. We can perceive materials by looking at something. You can see whether it's something breakable or not by just looking at its shininess, for example. You can guess these things. You look at the geometry, and with that, the brain also makes up lots of recognizes objects, locations, events there, and after we recognize things, the brain takes action. So this is how actually this is about cognitive science, how the light field is perceived. Again, we are not going to focus that much on this part of this course, but yeah. Here we are going to focus more on display devices in this first week's of class. So the graphics algorithm, since we are looking at our output, we are going to be generating images. We need to take into consideration the display device and the viewer's capabilities. For example, we don't need to render an 8K image if the target display device is 2K only. No need to render tiny details that cannot be perceived by a human. So we need to take into account these things. For example, if you may know the Apple, for example, they just have these retina displays. There is nothing retina about those displays. It's basically saying they have this fancy name retina, saying that that's the, if you view that screen, for example, 20 centimeters or 50 centimeters from you, the human retina cannot see individual pixels. So it's the highest resolution that you need at 20 centimeters. It's just basically a certain resolution. It just say, okay, this is for example, 4K resolution image is sufficient when you're viewing it 20 centimeters from you. It doesn't mean that display is going to be sufficient when you use the same resolution in a VR virtual reality headset, because in a virtual reality headset you are actually zooming with the lenses, and you're seeing the display much closer. So if you put a retina display on a VR headset, yeah, you may get to see the pixels, all right, no longer retina. Yeah, so 720p or 180p, they're also large resolutions. And by the way, these usually, the resolution is indicated usually by as megapixels, which gives us the total number of pixels in an image. And when you say total number of pixels in an image, it's you have the number of pixels at the columns, number of pixels at the rows, and also you need to have the aspect ratio. Is it a rectangular image? We usually have these days a fixed aspect ratio like 16 by 9 is the widescreen is something that is now common these days. Earlier, for example, if you look at televisions in 1960s, 70s, 80s, or in 1990s, the display was not 16 by 9. It was more like 4 by 3, more like more closer to a square. But usually the megapixels tells how many pixels are there in total. And the 700p, I think it's the, I always mix these things. It's either the number of pixels at the rows or the columns. Can anybody clarify that? Yeah. Yeah, exactly. It's by height. Yeah, it's the 720p is the height. So actually, they can be. It's just a convention. They could be. I mean, if the image quality is measured by megapixels, it's the. I mean, 720p actually means that it's the if it's the height. If that's 900. Sorry, that 16 by 9. Okay, it's like this. 16 by 9. So this 9 is 720 pixels. Sorry, 720. How many pixels? So it's basically a linear. There's a linear relationship between these two things. So the number of pixels at the width is going to be this question mark. If you just multiply this width and divide it by 9, you will get the number of pixels in the column. So if you multiply these two things, 720 multiplied that number is going to give you basically it's going to give you the number of megapixels, the pixels you have. Yeah, it's 1280. So if you multiply 1280 by 720, it's about 1 megapixels. Yeah, so a 720 image, 720p image is a 1 megapixel image. They're just interchangeable things. All right. So 180, I think it makes 1980, right? 1980, something like that. So it's around 2 megapixels then, right? I mean, a 180 image. I mean, it's just everything is about pixels. And a year ago or 2 years ago, I got a message on my office phone from someone calling outside. Basically, that person asked me, what's the size of a pixel? Okay, that really depends. You can have pixels. I mean, that's something different. For example, you can say 720p. What is the size of a monitor or size of a display device with 720p resolution? It really depends on the hardware, the pixel size. I mean, if you can have 720p on a smartphone, you can have a 720p on a big monitor. You can have 720p pixels on a big bulletin board next to the in the road. I mean, in that case, the pixels are going to be maybe 1 centimeter long, depending on how you have your those devices. Yeah. Yeah, 2 megapixels is like 180p, 1 megapixel is 720p. Yeah, so it's good to think about it that way. All right, but anyway, it tells us that the display is something discrete. We are trying to visualize something continuous. A light field is continuous, but the images we generate are going to be discrete entities. And 2 million, if you're going to generate 180p images in your computer graphics application, it means that you will be generating 2 million pixels at every frame. 2 million pixels. That's sometimes called a frame buffer. The frame buffer is that 2 million pixels that you have in memory before you write into it an image. Okay, before you write it as a PNG JPEG file, or we are going to be in our first assignment, we will not be using any JPEG library. Maybe we could use JPEG libraries or some libraries, but we will just be outputting a very simple image format, which is called portable pixel map, PPM. So PPM images, especially ASCII, in ASCII, they are really inefficient. They will take lots of megabytes in your hard drive. Portable pixel map is basically you just, for every pixel, you write the red, green, blue values, the RGB values as ASCII 3-character values from 0 to 255 for every pixel. So if you have 2 million pixels, you are going to have like around 20 megabytes or something. I'm not sure. So you think about the spaces in between them. For every pixel, you need 3 characters, 3 bytes per color channel. There are 3 color channels, RGB, but not all of them are 3 digits. Some of them, the first 100 of them are 90 of them are 2 digits, 10 of them are 1 digit. So if you just look at the average number of values you have, but imagine we have an image which is bright. There are no colors, color intensity is less than 100 values. So we will need in that case 3 bytes per color channel and 2 spaces and 1 end of line. So add 3 to that, so 12 bytes per. If you write them line by line, we can actually have space. Anyway, just around 12 bytes. 12 times 2, 24 megabytes. It will be like 24 megabytes of space just for a 2 megapixel image PPM. So it's really inefficient. But we will do that. And actually, there is a tool called Image Magic. I'm writing it in chat box. I think it was spelled like this, Image Magic, which allows you to convert different file formats from each other. It's available on Windows, Linux, and in your program, you can make a system call to Image Magic and convert your PPM to a PNG and save it like that and delete the PPM file. So you will be able to see your algorithm's results, your image, as a PNG file or a JPEG file with that. And also when we talk about these images, we will talk about lossless compression. So JPEG is a lossy compression algorithm, image. We will have some it's an algorithm that actually tries to make some lossy, it loses some of the original color values, but it does that in such a way that human perception does not get these losses. Humans do not perceive these losses, so it tried to do that without just sacrificing the image quality. All right, so yeah, display devices and perception are like that. So images are an image, sometimes also known as a frame. It's just a static single entity. We send them to a display device, and if we send those images fast enough, 60 frames per second, we will get ourselves a video. And sometimes you can combine those images together to have your store video offline for yourself. And for that, we also get into video codecs. In order to have a video, do we really need to have 60 images per second for every video? If we did that, videos will be too large to save on our hard drive. So maybe we store just keyframes every second or every couple of seconds, and sometimes maybe have some kind of a nice algorithm to find the differences between those images stored to indicate to save space. So really this is something else. So images and videos, have to store them, compress them efficiently. That's not the focus of this course. And by the way, since we talked about images, I want to also talk about the difference of computer graphics from image processing or computer vision. They are really two different things. computer graphics, the input is 3D, a virtual world or a model of a real world, and the output is 2D. In computer vision or image processing, the input, on the other hand, is a 2D image taken from a real camera. For example, our goal is to make some interpretations, understand the 3D world that this 2D image was captured. In other words, the output is like 3D in computer vision. For example, you have a stereo image in computer vision. You get two images as input, and you try to, for example, count the number of humans in that image. That's some kind of, it's not a 3D information, but it's some kind of semantic meta information about the image, about the video. So this is what computer vision is trying to do. It tries to make computer see by getting input as the real world video feeds of the real world. So they are really doing the reverse thing. Computer vision takes images, try to infer something about the real world. But in computer graphics, we get some 3D world, that's our input, and we try to generate an image. All right. Yeah, the highest frame rate the eyes can perceive, it was known to be around 30 frames per second. So if we usually when we have, I mean, our televisions, I think there are different systems, the NTSC, PAL. I mean, the frequency of the television screen was about 25 frames per second. So 25 frames per second, if we see something at 25 frames per second, we usually perceive it as smooth. But there are also things like how fast the things are moving in the image. If you have a video in which something is moving very fast, you may need higher frames per second, like 60 frames per second. People use 60 frames per second these days. And in some games, for example, you try to achieve 100 frames per second. But usually when you have something around 25 to 30 frames per second, we can perceive it as smooth. Yeah. Oh, does it depend on the different people how the frame rate the eyes can perceive? It may also not the same. It may not be the same in every location in front of our eyes. Maybe the frame rate at the peripherals and at the front may be different because we have different kind of cells in our retina. Some of them are better at perceiving motion. Some of them are better at perceiving color. For example, the rods and cones. These are what I'm talking about. So it may change from different places. Maybe it may. Are there some genetic factors that affect this? Maybe. I'm not sure. So it goes into lots of eye biology that I'm not an expert of. So yeah, there may not be. Yeah, there's but as I said, the highest frame rate. I mean, in real life, also that's another thing. In real life, what's our retina doing? Does our retina have some frames per second? I don't think it's like that. I think it's like it's excited. Some signals come to the retina, and it remains there. For example, if you look at a bright light for a couple of seconds, and if you look somewhere else, you will still see some brightness. So it's just light rays, photons exciting some sensors in your retina, and they have some continuity in themselves. So if things change very rapidly, still our this retina biology will not allow to perceive these changes smoothly. The photons from the previous exciting effect is going to remain in your retina. Your retina cannot immediately switch to this thing, but it's all about photons and how they interact with your retina. Yeah, the difference between 30 and 60 frames per second may be obvious, but in some videos it may not be that obvious to everybody. I mean, it really depends on how fast things are moving in the image as well. So, oh yeah, there's Umut shared test like a benchmark, I think, site testufo.com to I think you can check that out if you want. So yeah, we need to take into account the images display, the hardware, and the human visual system. So how we perceive things is also important. So yeah, this is the first weak part, is images and displays. The visual perception, we will just talk a little bit, but that's not the focus of it. We'll just spend 1 week on these materials. The actual material will be to, by the way, I just remembered I was talking about something, and I just forgot what I was talking about, and I just jump to another subject. I was talking about this piece of orange. Let's get back to that. So let's see, we still have 15 minutes until the break. So I was talking about sometimes we do cheating to speed up things. And I was talking about this orange, in which it has, if you represent an orange as a perfect smooth sphere, and you want to have some bumps on it, okay? So oranges are not perfect sphere, they have some bumps on it. So if you try to modify, you can do that by 2 things with geometry, modifying the geometry, but it may take some time. I mean, trying to model the orange like that. So the way we cheat actually in, this is an example of cheating in computer graphics, is to play with the normal vectors of the sphere, okay? In mathematically, the normal vector on the surface of a sphere is the vector from the center to that point, okay? If you just draw a vector from the center of that sphere to a point on that surface, that's the normal vector. The normal vector actually is a vector that tells us at which direction that point on the surface is looking at. Why do we need this normal vector? This normal vector is really important to understand the amount of light that is bouncing off this point. For example, if there is a light at this location, we know that with physics, if you have a surface point which is directly looking at this light, all right, if there's a surface point that is directly looking at this light, the light is going to bounce off more from that surface point. The light is going to bounce less from this surface point. So how do we cheat? We just perturb these normal vectors, do not use the real spherical normals. When you perturb them, although the surface is looking this way, you say that, okay, let's have a normal that is looking this way, all right, which will achieve some effect, like there are holes in it, or it's in terms of shading. This is not called shadow. Light still is perceived from that, but the shading of that region is going to be darker than the others, so it will have a bumpy effect. So this is also called bump mapping, having this normal map. So we usually have images like this, 2-dimensional images, which tells us the normals are this. The normals on this surface are all these different directions, and we actually map these different direction normals onto the sphere so that it looks like an orange. All right, it's not totally random. This bump map, the norm, sometimes called normal map, is something again designed by a human modeler, so that it looks like an orange. The number of holes or the cavities in an orange is different than the cavities on the moon, or where the cavities are going to be on the moon it may not be regular. So we may have some large holes, some small holes, so it may be like that. All right. So most of the course will be focused on rendering. All right, and animation, I don't think we will. If we have time, we will touch upon animation, but we usually do not have, at the end of the semester, we usually do not have enough time to talk about animation. All right, so let's start with images. I'm going to go through the next set of slides quickly. Images and displays. And then in 10 minutes, we will have our first break. So let me change again to a pen. So I'm going to skip through some of these slides quickly. As I said, this is you can just read some of the material by yourself later as well. I'm just going to focus on the important parts. Some of them are repetition. A video is an image sequence. Our output is images basically. So an image is just a rectangular light field actually. So this is a continuous image. So when I say a light field, it has a width. Okay, an image or a frame has a height and width, and this height and width, the relationship of this width and height with pixels may be different. If our pixels may be square or not, we may have rectangular pixels. Okay, so it's really the pixel width and height is also something that should be given to you, and also this height and width. When it's given in terms of some world coordinate system, it should have some units. Is it 1 meter, 2 meter? What's the but basically, an image is something rectangular, but that's not real. I mean, you can have images that are spherical. You can have images that are triangular or hexagonal. I mean, you can have different display devices. I mean, if you're a hardware manufacturer, why not have televisions that look like hexagons, for example? You can have that. Okay, so this restriction is really not physical. I mean, it's real life physics does not tell that an image should be rectangular. This is how this is the most common digital image. That's why we call it as rectangular. Okay, probably our retina is not rectangular. Okay, it's probably something more like a spherical, or it's curved most probably. So here and height and width and any position here can also be continuous. Given any point xy, what is the intensity or light field at this xy, we can have continuous images. But in real life, we because of the restrictions of digital computers, we need to discretize this image into pixels, and what we are going to store at those pixels are also going to be important. Are you going to have grayscale images or bitmaps by just two colors, white or black at every pixel, or some colored images, and how are you going to represent that color? So usually an image looks like this with square pixels. The pixels aspect ratio is 1:1. Here it's a square. Pixel comes from picture element, and the number of pixels is given usually by number of as height times width, or which is going to give you the total number of pixels in an image. This total number of pixels in an image, sometimes called the resolution. But in order to indicate resolution, as we discuss, we sometimes use just the height of the image as its resolution. So the data type that is stored could be just zeros or ones. We will have bitmaps in that case. It could be grayscale. We may have just a single channel information, sometimes called intensity image or grayscale image. And if we store just 1 byte from 0 to 255, we can still have very nice looking images with just these 256 different grayscale values. And color images, the most common images that we see these days are color images, and usually they come in 3 channels. We use 3 different color channels to indicate color. And the most common one, and we will be using that in our course, is RGB, red, green, blue channels. And each of these bytes is going to tell the amount of red in your pixel. Given a pixel, we will have 3 values: RGB, R, G, and B, and the amount of 255, 255, 255. If all 3 of them are 255, we will get white. If all of them are 0, we will get black. And if they're all equal to each other, if red, green, blue values are equal to each other, we will get grayscale, a gray color. And if our red is high, for example, if you mix red and blue, you will get purplish color. If you mix red and green, you get yellow. If you mix green and blue, you get cyan or turquoise. So there are different color names. And In generalized images in which we have not digital, so this from the real coordinate system, the image coordinate system. So this r square, we didn't actually yet, if we have images that are from r squared to r cube, it means we didn't discretize our pixels yet. They are real value. The image coordinate, we will talk about something like image coordinate, that is, if it's a continuous value, which means that we have a continuous image. But we'll talk about pixel coordinates, in which we will just consider the center point of the pixel, whatever it is, as the pixel coordinate. All right. So given since pixels will have certain widths and heights, the center of the pixel, whatever that continuous value is, we will use that as the pixel coordinates in many of these algorithms that we will discuss. So here's an example. Bitmap image doesn't look that good, all right, but it's still, you can still see things here. And here's a grayscale image, a cute puppy. Here, as you can see, it's really, you can perceive a lot more, a lot detailed compared to these bitmaps. People use different techniques. When in the early earlier days in 1970s or 80s, there were techniques like dithering. You can take a look at that. With just bitmaps, with just single bitmaps, actually white or black, you could have an image which have this grayscale effect by having certain parts changing from gray to gray. Red and black mixed. White and black mixed together. The human eye perceives those regions as gray, so you can achieve like grayscale looking things with just bitmaps. And I think this is JPEG. It doesn't look like a bitmap to me. I think people, this is not a bitmap. There are some grayscale values. If you look closely to this image, it's not totally black and white, right? I can see gray here, definitely. And the reason because this seems like gray is probably, it was originally maybe a bitmap image, but after JPEG compression, when JPEG compression, as I said, it's a lossy compression. It takes averages of pixels around in some neighborhood. So when you take average of white and black pixels, what do you get? You get gray. Okay, so this is actually looks like a grayscale image. So there's a question: hue, saturation, and value, sometimes called HSV. So there are different color spaces. There is luminance, I forgot about this. But yeah, the most common one, the one I use is RGB. There is hue, saturation, value. Hue is like the type of the color is indicated in hue. Saturation is the value, how much of that color you have, and value is like the intensity. So there are different color spaces. RGB is not the only color space. We are going to talk about that when we come to images. In terms of compression, or I think in terms of how humans perceive things, I think some of those color spaces better map the human perception if you display those values in. It's still 3 channels, but they represent different things. Yeah, so there are implicit formulas. There are closed form formulas which can take hue, saturation, value and convert it to RGB values. So they are mappable to each other. One color space could be mapped to another color space easily. And the interesting thing is that in real life, their actual color, it's not 3-dimensional. It's 1-dimensional. The only thing that determines color of the light is its wavelength. And wavelength is just one entity. There is no RGB. But based on a certain wavelength light, but we have RGB. You can think about, we have RGB maybe in our retina. Certain wavelength lights could be perceived by red cones, some other. We may have these different channels in our biology, but the actual light itself is not. It may not be three channel. There's only one thing that determines the color, and that's really interesting. How this single-dimensional wavelength, as it changes from um, ultra, I, blue to red, and how it changes. So from infrared to ultraviolet. So how these wavelength changes the colors. That's really interesting. And this is a color image, 24 bits per pixel. So this BPP stands for bits per pixel. And at this point, we may have our 10-minute break. All right. So before I continue more in color and how we store them inside these pixels, let's now have a 10-minute break, and I will continue after the break. Any questions before we go into break? All right. See you in 10 minutes then. I will stop the screen share, and I will stop the meeting. See you all in 10 minutes. Oh yeah, I record the lectures, and I will post them on YouTube unlisted. So you will have high quality videos this time.